So hi, everyone. Welcome to the Deep Graph Learning series. So today we will learn about some foundational aspects and properties of graphs. So this is an introduction into the classical world of graphs and graph presentation. So we will look at graph types, properties, and graph learning tasks. So let's start first with graphs. So graphs are actually very powerful representations that we can use to kind of encode data. So we code data into matrices. There are tools that we can use to model interactions or relationships between different elements of a system or of a particular data set or a particular environment. So by modeling such dependencies or interactions in a reliable way, so it's a very important keyword, reliable way, we can derive rules, we can do predictions, we can also discover new knowledge about the system that we are studying. So graphs are actually very powerful. They're also very prevalent. A lot of real world data manifests in graphs. Like for example, here, we can see that A represents road networks. We have in B molecules. So this is a molecule. We have in C electrical circuits that are naturally structured as graphs. So we have a bunch of nodes and a bunch of edges with different connectivity types. So you can see here basically that we do have different, different real world data that can be encoded or represented into graphs. So adding to that, for example, social networks, they are considered as graphs where nodes represent people and edges represent, for example, friendships or the type of relationship, the relationship between them. The scientific literature where you publish papers, you can model it as a graph where the nodes denote or represent papers and the edges represent, for example, citations, which means, for example, a paper A, okay, will cite a paper B. So Wikipedia also is a graph where nodes represent articles and the edges represent hyperlinks between articles. So if you have, for example, article 1 and article 2, so you have these kind of hyper edges that connect these two articles. Computer programs can also be represented as graphs. So it's everywhere from social networks, scientific literature, to programs that we're coding up where nodes are syntax tokens. For example, they can represent variables. A node can represent a variable at a particular point in the program flow, and the edges, they represent computations involving these variables. So if you have two variables, for example, x and y, so these are the computations that happen, like these are the type of computations that we can add as edges or encode as edges. For example, multiplication here, so we can multiply x by y, okay? So also geometric point clouds can be represented as graphs. So here each point on the cloud is a node and has edges, and these edges, they connect this node to nearby nodes. So you have this kind of, structure where you have a bunch of nodes that are kind of connected in a directional or undirected way. So we're going to see the types of graphs in a bit. In biology or in microbiology, we have proteins. So protein to protein interaction. There are lots of data sets that we will see during this course. For example, PPI, where you have protein to protein interaction, they can be expressed as graphs. And the nodes are proteins, and the edge between two proteins exists if they do interact. In the lack of interaction, there is no edge. Okay, so you have different types of proteins, protein 1, protein 2, and you have, for example, this is protein 3. So you can see that protein 1 and 3 do not have an edge, so there is no interaction between them. Okay. So the world is teeming and boiling with graphs. Like graphs, we can use them to model the world at both macroscopic and microscopic levels. So you can see here the macro is the road maps that we have, okay? The micro is a molecule, And also, if you want to call this a mesoscopic scale, so you have a circuit here that is like, that represents or encodes, for example, a mesoscale data. So there are more examples. So let's look at these examples. There are different various types of graphs. And the first one here is a social network. So here we can see a social network where you have different people, Alice, Bob, Carol, etc. And the interaction or the connection between them, you can see that they are symmetric. So it means if there is no sense of directionality. So if there is an edge here, it means Bob is connected to Carol and Carol is connected to Bob. So basically the relationship here is symmetric, and this is what we call an undirected graph. So in this example, this is a particular type of graph where you have, for example, friendships on a social network. So B, let's look at B. B here is a citation network. So in this case, the network is actually, as opposed to the social network, which was undirected, this is a directed graph, okay? So a directed graph, it means that we have one node pointing towards the other node and another node. And this directionality can sometimes, it is not symmetric, which means you have only one directional flow of information or connectivity from node I to node J. So in this example, this is a citation network. So you can see a bunch of papers here. So each node represents a research paper, and the edge actually encodes that, like a publication cites the other. For example, let's read this together. So you can see here that this paper has cited, okay, so this paper has cited 3 other papers, okay? So if we look at, the Watt et al. 1982, this paper only has cited this paper, and it has been cited, also if you read this in a reverse way, it has been cited by Hain 1985, okay? So you guys can see that this relationship means cited in, so we can also define reverse the graph if you want to reverse the relationship or the meaning of the edge that you're defining. So another type of graphs here, let's look at this. So C is a knowledge graph. So a knowledge graph is actually a directed heterogeneous multigraph. So we will learn about all these types in a bit. So what is a heterogeneous graph? What is a directed graph in more detail? So here I just wanted to give you an overview of different graphs before we get started. We dive into the theoretical definition. So in this case, in this knowledge graphs, you can see that in this knowledge graph, you can see that the nodes are actually heterogeneous. So we have different types of nodes. So this is a person, Bob, Alice, Aaron. You have a country, Canada. You have Google, a company. So the nodes have completely different types. So we call them heterogeneous nodes. So we have heterogeneous nodes, okay? So this is heterogeneous nodes, okay? And then they represent different object types. I mentioned people, places, companies, and there may be multiple edges representing different relationships between each node. So for example, multiple edges, it means 2 nodes, like for example, Alice and Aaron, can be connected by 2 different edges. So for example, here, if we look at Bob, let's start with Bob lives in, so that's the meaning of the edge. Canada is a customer of Google and works for Google. So you can see that here we have a multi-edge. We have 2 edges that connect the nodes Bob and Google. Okay, so that's, we call it a multi-edge, and that's why this is called a multi-graph. So now in D, we see another type of graph. So here it's basically a point set, which can be converted to a graph by forming edges between nearby points. So each node has an associated position in 3D space, and this is termed a geometric graph. So in this case, we have a geometric graph where we actually convert a cloud of points based on the distance between them. If they're close, we will define an edge between them, okay? And this is how we can mesh, for example, a cloud of points. We can transform a cloud of points into a mesh or a geometric graph, because it has spatial neighborhood, okay, or interpretation. So spatial graph or geometric graph. Now, the last example in E, we have here a hierarchical graph. So this represents actually a scene. And you can see that this scene right here, so let me change the color. So this scene right here where you see a room, light, and table, there are 3 items. And these 3 items, they can be represented or encoded into a hierarchical graph. So the topology of the room, table, and light are all represented by graphs. And these graphs form nodes in a larger graph representing object adjacency. So you can see, for example, in the room, you have the ceiling, you have the back wall, the left wall, you have, floor, etc. So you can connect these depending on the meaning of maybe spatially, if they are kind of spatially adjacent, right? So there is a meaning that you need to assign to this edge to be able to connect these nodes. For example, when you have the chord and a light shade, so you can see here they're spatially connected. The chord and the light shade, they're connected together. So you have in the light, you have 2 nodes which are spatially connected directly. And then for the table has, legs. So these are sub-elements like 4 legs. So the top of the tabletop is connected to 4 other elements. So this is a tabletop and you have 4 other elements. So you guys can see that, this is a very, there are different ways of representing graphs. And we can define these. We can define these properly. Directed, undirected, multi-graph, heterogeneous graphs, hierarchical graphs. So first, we will start by exploring together different graph types, and then we will move into graph properties, or the graph matrix properties. So this is the second part. And in the last or final part, we will cover different learning tasks, particularly graph-based learning, node-based learning, and we have edge-based prediction or learning. So we will cover all of these today. So let's start first with the graph types. So the first type here is, we need to know when we use graphs if the graph is directed, undirected, binary, or weighted. So it's actually very simple. So a graph is encoded into a matrix. So maybe I need to take a step back and introduce to you matrices. So right here. So a graph is actually encoded, is defined as a tuple of a matrix. We have encoding matrix, we have a set of vertices and a set of edges. Okay, so the set of edges, you have an edge, that EIJ, that belongs, that connects, basically connects. It's a set of edges, connects node I to J in the graph. V is actually the set of nodes of the graph. And A is we call it the adjacency matrix, okay? So the adjacency matrix, where we encode, the relationship between these nodes. So I'll show you in a bit. So we represent the graph, visually by drawing a bunch of nodes and connecting them by a bunch of edges, like here. So this is our graph. And in this graph, we can see that we have 6 nodes, 7 edges. So each node has associated what we call embedding of length 5. So the brown vectors. So the brown vectors here, we call them, because we're going to do deep learning, we will call them embeddings, okay? But you can also call this vector not just an embedding vector, you can call it a feature vector, or you can call it an annotation, a node annotation. Okay, so there are different names that we use to define these values or these vectors that are assigned or allocated or or stored for each node in the graph. Okay, so this graph can be represented by three matrices. So what are these three matrices? So first, we have the adjacency matrix. So here in this case, it's a binary matrix, which means the connection belongs to each element here, belongs to either 0 or 1. And, you know, an element, for example, Mn is set to 1 if the node M connects to node M. Okay, so that's very easy. So you can see that, for example, if we check node 3 and node 4, so let's use a different color. So node 3 and 4, so we have 3 and 4, and you can see that these are connected. But if you select, for example, 3 and 5, there is no connection between 3 and 5, so it's empty right here, okay? So this is the adjacency matrix. It's of dimensionality. It belongs to Rn times n, because n here denotes actually the number of nodes in the graph. And it's a matrix that encodes the whole graph. I call it the heart of the graph. So this matrix, we will use it to do so many things. Learning, information diffusion, discover the resilience of the graph, discover the efficiency of the graph, the topology, the patterns in the graph, the organization of the graph, the most important nodes, the most important pathways. So this matrix, basically, it has it all. It has everything we need to know about the graph. Now, if we do have an additional information, which is the annotation here. So in this case, we see that we have an additional matrix, the Brown matrix, and this matrix actually is it stores the embeddings, or it contains the concatenation of these node features. Okay, so it's a D by N matrix, which means D is the number of you know, the size of the embedding. Okay, so here we have the D, and then we have 6 nodes. This is the number of nodes N. Okay, so these are nodes, and this is the size of the embedding. So we have 5 embeddings, 5 values in our embedding vector. So when we take all these guys, all right, so we take all the node features, in our graph, so all the brown ones right here, and we stack them vertically, we get what we call the node data matrix X. So now when we have a graph that is annotated, we're gonna add these, you know, these feature matrices, and it add another layer of information. So we don't only have the topology encoded by the adjacency, but we have an important additional information, which is what are my nodes storing? So maybe this node may be topologically important because it has 4 connections, right? So it's well wired, it's strongly connected to other nodes, but it may not be very important or relevant because its features are kind of low values or low qualities. And, you know, it may kind of, you start looking at the graph from a different perspective. So you have here 2 things to look at the graph. You have the adjacency and you have the node data matrix. And now we're going to add another layer. So the third the third matrix that we will add is, let me just remove all of these just for clarity, is actually the edge data. So the edge data matrix E, it stores the edge attributes or the edge features. So now you can have what we call annotated edges, which means for each edge or each connection, I'm going to use smaller. So for each connection, I will assign what I call an edge embedding or an edge feature that different types of attributes. So this connectivity type have different additional values that I am collecting, I'm initializing, I'm defining, and then we're going to stack them also all vertically. So we have E connections here. So these are the number of edges. All of these are actually edges. And these are the attributes or the features of the edges. So now in this graph, this is like a graph that has 3 different important matrices. The most vital and important one is A. So you cannot define a graph without an A. You cannot get rid of this, okay? That's not possible. You can get rid of the features. You can remove the features assigned to the nodes. You can remove the edges, the edge features assigned to the edges, but you still need the adjacency matrix because you will use it to define the graph, okay? Cool. So I think now we have an idea about how to represent graphs into not only a single matrix, but a bunch of matrices. And let's move to the different graph types, okay? So a graph is, so I'm going to just quickly explain this visually because we will cover it in a bit using matrices. So here, a graph is directed. If there is a direction, in which a node I maps or connects to a node J. So this is, for example, a particular type of connection. We can add more nodes here. So I can add the node K, and you can see that, you know, in this case, we have this kind of directed graph. We can also change the directionality. It means that K connects to J, but J doesn't actually connect the K in the opposite direction. So it's K that connects to J in a particular direction. So that's a directed graph. So this is directed graph. Now, undirected graph, it means here the EIJ is equal to EJI. So we have, if you think about this, you know, edge as a decomposition or concatenation of both edges, which means both nodes connect to one another or to each other in both directions. And in this case here, is actually we have EI towards J, and we don't have, you know, we don't have EJ towards I. So this doesn't exist, okay? So the other direction doesn't exist. So in undirected graphs are very easy to kind of, you know, process because you have, you either have a connection or not. You don't care about the directionality of the connection. So I can add a bunch of connections here, and all of them will be, you know, undirected. So it means all of them are connected in both, you know, in opposite directions, okay? So now, what is binary and what is weighted? So binary, it means you either you assign either a value of 0 or 1 to the edge. So here it means that the edge weight can only be of 0 or 1. So for example, the EIK is equal to 0 because these two are not connected. But you can see here that the EK to J is equal to 1 because it is connected, okay? So that's a binary graph. Now, a weighted graph, it means that the edge weight, so the edge weight, if we call it Wij, so can belong to R. So for each I and J in the node set V, okay? So in this case, for example, we have Wij, it could be 0.5. And then if we look at this connection right here, we can have a completely different number. So for example, 0.9 with this node, let's call it K, okay? So Wik is equal to 0.9 and Wij 0.5, and you can take any value you want, negative, positive. You can even make negative values if you want. So your graph is weighted. It can take any real number. It can have any real number assigned to its connectivity strength, connecting pairs of nodes, okay? Cool. Now we move to the second type of graph. So this is also an important definition. So the definition of a simple graph. So what is a simple graph? A simple graph is a graph that has no loops or multiple edges. So we call a graph simple if it has no loops or multiple edges. So a loop in a graph is a self-connection, which means an edge that connects up to the same node, okay? A multiple edge, it means that two edges that connect the same endpoints or actually more. So they can have, you know, we can have, for example, we can add more edges. We can have a third edge here or fourth edge. So this is a multi-edge, okay? Which means two nodes are connected not only by a single connectivity type or a single edge, but by a set of edges. So we have 1, 2, 3, 4 types of edges right here, okay? So for example, you can think about cities. So if you drive on the highway, there are 2 directions. So there are 2 routes connecting 2 cities, and that's considered as a multigraph. You can model it as a multigraph, okay? So if we call the graph simple, it means it doesn't have loops, and it cannot have multiple edges. Now, complete graph. What is a complete graph? A complete graph has each of its nodes connected to all other nodes. Okay, so it's a fully connected graph, which means it is complete in connectivity or in topology, and every 2 nodes are adjacent. For example, if I take this graph and I draw these guys here, so is this a connected graph, a complete graph? No, it's not, because I'm missing connections. So I need to complete all the connectivity. So these 2 need to be connected, right? So, and this one too. So basically, for each node, if we have, n nodes in the graph, so if we have n nodes in G, then each node I connects to n-1 nodes if we exclude self-connection. But if we add self-connection here, so the graph is not simple anymore, then it becomes, to n nodes, including self-connection. Okay, so that's a complete graph. And here we don't actually stipulate that this. So we don't need the graph to have the self-connection. So that's actually an additional point. But if this condition is satisfied, then the graph is actually complete. Okay, cool. So now we move to the 4th type of graphs, or the 4th definition. So we have a subgraph. So how do we define a subgraph? So a graph is composed of different smaller graphs, or what we call subgraphs. Okay, so we examine, for example, by examining the structure of graphs, we can define different subgraphs inside it. So the subgraphs actually do allow us to examine the structure of graphs that lie within a given graph, okay? So a graph H is called a subgraph of G if every vertex or node and edge of G belong to the graph, okay? So which means we need to extract all edges that are connected to that subgraph, and also all edges and all nodes, to make sure that it is actually a subgraph. So here a graph G is a subgraph. Of course, if you look at the graph itself, it's a subgraph of itself. So we can consider, G as a subgraph of G itself. And all other subgraphs, we call them proper subgraphs. Okay, so they're called proper because here B. So we're called them proper subgraphs because we need to extract them not from the main graph, but we decrease the number of edges and the number of nodes. Okay, so another definition. So if H is a subgraph of G having the same vertices as G, then H is a spanning subgraph of G. So which means, for example, let me give you an example. So here, H is a subgraph of G having the same nodes as G. So which means H must have these 5 nodes. Okay, we call it a spanning subgraph if, for example, we take here, so let's say we do actually have more connections. So I'm going to add another node right here. So let's say we have a node 0. Let me start with add a different color. So just, to make things more consistent. So we have a node 0 here. So if you guys take, basically these, this graph, so you can see that actually this path right here is a subgraph, you know, a spanning subgraph of G. Okay, it's like one a potential backbone of G. All right. Now there is another thing that we may want to think about is that these subgraphs, they allow us to extract patterns and different pathways in the graph, and you know, they allow us to kind of check if the graph has different patterns or different kind of, you know, particular topologies. Like, for example, you can ask the question, how many triangles I have in my graph, okay? Or how many squares I have in my graph, like this, something like that. So these are, you know, important questions because they allow us to extract what we call patterns and to read the graphs in different ways. So this is just a simple definition of a subgraph, but then we can, we will revisit these during the lecture, the future lectures. So induced subgraphs. So what is an induced subgraph? So now we're taking it to the next level. So we're looking not only at graphs, but what we call an induced subgraph. So given a non-empty set S, so this is an non-empty set of nodes of G, the subgraph G of S of G induced by the subset or the set S. So now it is, the graph is induced by a set of nodes, okay, has vertex set S where two vertices U and V are adjacent if and only if U and V are adjacent in G. Okay, so this is a bidirectional statement, which means if we read it in the opposite way, if U and V are adjacent in the graph, they should be and they must be adjacent in the subgraph induced by S. So let's look at this example. So I want to take a minute, guys. I want to take a minute and to figure this out, okay? So here we have a graph G. Now I define two subgraphs, H1 and H2. So what I wanted to think about is which of these graphs is induced, okay? Are they both induced? Maybe one of them, maybe none of them. So we start first with the definition. The definition states that we need a set S of vertices. So here the set is defined by these nodes. So I'm going to node W, V, and we have X and Y for these guys. And now for the other graph, for the second graph, so I'm going to choose a just a circle. So we have U, V, X, W. So we have U, V, U, W, X, V, okay, or U, V, X, W, okay. So these are the two graphs. Now, when you look at these, you need to check this statement, okay? So if U and V are adjacent or are connected in G, are they connected in H2 or in H1? So you need to check all the connectivities between these pairs of nodes, between the red ones and between the blue ones individually. And if you discover that one node, for example, in the original graph, two pairs of nodes in the original graph are connected, but they are disconnected in the subgraph, it means that that subgraph is not induced, okay, from S. So it's not an induced, you know, from G by S, by the set S that we define of nodes, okay? So let's take just, you know, a few seconds to think about this, and I'll give you the answer in a bit. So the answer is that H1 is actually induced by the set of that we selected here, this set of nodes, and you can see it's because it actually includes all the connectivities that we have between these nodes, immediate connectivities, okay? So you can see that all of these guys are connected. But if you look at the H2, so what happens for H2 is that if I, you know, remove these values, so what happens is that for H2, there is an edge right here that is missing. So V and W in the set, they are connected in the original G. So hence they need to be connected in an induced graph. So this connection was actually missing, and that's why H2 is not an induced subgraph by S, okay? All right, so let's keep moving. Now we're gonna move to the next definition. So we looked at directionality, weighted and binary graphs, simple, complete subgraphs, induced subgraphs, and now we're gonna look at annotated or decorated graphs. So annotated or decorated graphs, this is what I presented earlier. So here, so there's like a bit misalignment. So we could just fix that a little bit. All right, so you guys can see that when we have an annotated or what we call a decorated or an annotated graph, it means the graph has, annotations or features that are assigned to all of its nodes, okay? So basically now the graph is defined as a subset of V, and the feature matrix assigned to the nodes V. So V is of size of N is the number of nodes. X is a matrix of size N times D, which means N nodes. Each node has D features or D attributes, okay? And E here is actually the number of edges. So when we have a fully connected graph, the maximum size should be N times N if we include, of course, self-connections, okay? So if the graph here, if we include self-connections, and if we do have directionality, so the graph is directed, all right? So if we have an undirected graph, so that's something I will add later, so I'll explain this later. How do we calculate what is the number of edges in an undirected graph? So anyway, so here we have the number of nodes, the features, and this is, for example, a graph that we have. So let's draw an example. So let's say this is our graph. So we have this type of graph with different connectivities. And we have an annotation here. So this is a feature vector that we will assign to each node. And we duplicate that, so which means for each node, we're going to store D features, and D could be thousands and thousands of features, depending on which, how do you extract those features, their meaning. It could be, for example, V here could be an image, right? So you have an image, and then if you take this image, the image of the tree, and it has, for example, 100 pixel by 100 pixel, and then you vectorize it, then you're going to have 10 to the power of 4. So you will have, lots of values over there. Okay. So here in this example, we have this graph. So the question is, what is the dimensionality of X? So think about the dimensionality of X. So X has basically, we said we have 4 nodes. So it should be, we have 4 here, the number of nodes that we have, okay? And we have the features, so actually a lower number of features. So we have 3 features, and we're gonna stack the features. So D is equal to 3. So every time we'll store these, feature vector, and this is the size of our X that belongs to R 4 times 3 in this example. Okay, so that's our, what we call a feature matrix. And later on in when we do deep learning on graphs, we will see that we will call it an embedding matrix. And why we call it an embedding matrix, so we'll discover that together. Okay, so it's a feature matrix assigned to this. So in this case, we have annotated nodes. We can also have what we call, as I mentioned earlier, annotated edges. And if you annotate the edges, it means you're going to have another feature vector here that is assigned to each edge. And this feature vector, we will create an edge feature matrix that allows you to basically store all these features into a single matrix. Okay, so we have seen this before, and this is nicely summarized in this example where we have the tuple A, X, and E, okay? So the tuple here, A, adjacency, X for feature matrix, and edge matrix, call it E here, all right? So we have different notations. Maybe with MathBF, it should be different from this kind of, set of edges. So here we have a set of edges, we have a set of nodes, and this is a matrix that connects, all the nodes via the edges. All right, so that's that. That's that, an annotated graph. So without assigning features to graphs, we will see that it becomes so hard to learn, to perform or do deep learning. So annotated graphs are a vital, I would say, they are vital for deep learning. Okay, cool. Now we move next to heterogeneous graphs. So our next stop is into a more complex. So we're going to dive into a more complex representation of the graph. And this is heterogeneous graph. So what is a heterogeneous graph? So a heterogeneous graph is a graph G that has basically a set of nodes like all other graphs. So all graphs have the set V of nodes. And in addition to that, we don't only have the set of nodes, we have the types of nodes. Okay, so V actually here stores nodes with node types. So we have VI, for example. I is a particular node, but it has a particular type right there. So we have different types of nodes. For example, people, companies, like we have seen before. So different types of nodes. And we also have what we call, edges with different relation types. So here, this is a triplet. And this triplet basically belongs to E. So every element, each element in E is a triplet. It has the input node, the output node, and if in the directed graph, and the relationship between these two nodes are. Okay, so we have a triplet here that encodes the relationship, encoding the relationship between pairs of nodes, okay, between pairs of nodes. And then next we have the type of the relationship. So we need to know which type of relationship we have. So we need to define this R. So here, the big set R defines all types of possible relationships. So this is the set that stores all possible relationships. And then the final one, T, is the node and edges that have features and attributes. So this is basically T. You can think about it as a combination of our X, the feature matrix, and the edge matrix. So feature node, let's write it down, node feature matrix, and this is edge feature matrix. Okay, so this is an example of a heterogeneous graph. So we have different types of nodes. So we have years, for example. We have the title of the paper. We have a paper citation, okay? The full citation or reference of the paper. And the paper has a title, it has a year of publication. So you can see here, these are the relationships that we have. So this paper is published in is actually the relation. It belongs to R. Has title, belongs to R. And you can see that here we can define the E, and the E between, if we call this node 1 and node 2, so 1, 2 is equal to a triplet, so which is V1, node 1. The relationship is has title, okay, and then V2. All right, so this belongs to our big E over there. So here, like I would say for a better notation, we should not use the same E here to denote the attributes. So these should be changed a little bit. So maybe for the sake of, mathematical consistency, we can use a tensor right here, or you can use, for example, mathcal like this to denote these, mathematical symbols differently, because they do not actually mean the same thing here. So we need to be careful with that. Okay, very good. Now, and for the sake of consistency, this is something that is always good for you guys to check. We can do it this way. All right. Now, the last type of graph that we will see is hypergraphs. Okay, a hypergraph. So what is a hypergraph? So now we're going a bit hyper. So we're going from, simple to complete to dichotomizing or dissecting a graph into subgraphs, then decorating our graph. Okay, so we decorated the graph, annotated it. We also added some complex relationships and different types of nodes to the graph, so it becomes heterogeneous. And we can model different heterogeneous relationships between different entities, completely different. And at last, we land onto the hyper world of graphs. Okay, so what is a hypergraph? So the hypergraph here, it models high order relationships among nodes. Okay, so what does that mean? It means that in a simple graph, in the regular graph that we have seen, all the other graphs, they are low order graphs. So I'm going to write it as like this. So this is different from typical graphs that model low order relationships. So a low order relationship, it means that you have two nodes and all that you care about is the relationship between these two, whether they're connected via one edge or multiple edges or multiple directional edges, etc. Okay, so this is still low level because you're only looking or zooming. We are only looking or focusing on the relationship between only two nodes. Okay, so a hypergraph is considered as a generalization of a graph in which an edge can join any number of vertices. And the set of non-empty subsets there, we call them hyperedges. So let's look at this example together. So first, we're going to start with a graph. So a graph here. So let's say here, if we have self-connection, if we allow for self-connection. So and I'm going to draw this graph. Okay, so let's see like this, make it simple. So let's fill this matrix. This is what we call an incidence matrix. So in an incidence matrix, the rows represent the nodes and the columns, they represent the edges. So here we have, let's call this E1, E2, E3, and E4. So we have 4 edges. So for the self-connected node right here, so it's a singleton. So it's isolated node. So we're going to put 1. So E1 connects only 1 and the rest are 0. Okay. So E2 connects a V2 and V4 and the rest are 0. And E3 so connects V2 and V3. And then E4 connects a V3 and a V4. So this is a regular graph. So in a regular graph, you see that the sum of the elements in each column can take only 2 values. So 1 or 2 here. Okay. So in this case, 1 for self-connectivity, which is an extreme case, right? It's it means that the node is here in this case is self-connected. You can also think about so this, you consider this as a single edge, you can have a value 1, which means self-connectivity. But typically, if we remove completely self-connectivity, and we say we want a simple graph, right? So in a simple graph, we do not allow for loops. So in this case, you're going to end up with having 2 everywhere. So here you can see that the sum is actually of these elements is 2 for each column. All right. So this is a graph. This is how we define a graph. Now, how do we generalize this, or what is it that we are changing or we need to change to make this a hypergraph? So I'm going to remove all of this. Okay. And then we will draw a hypergraph together. So let me take this example again right here. And here we go. So in this case, we're going to allow for multiple edges to be connected together. So let's say edge 1 here. So we have this. an edge can join any number of vertices. So I want this edge to connect V1, 2, and 3. So I will draw it this way. So V1, 2, and 3. And then we have, so this is what we call a hyperedge. Hyperedge E1. So, okay. Now we're going to do, we will try a different combination. So hyperedge 2 connects V1, 3, and 4. Or let's say a V1 and V3. Okay. So V1 and V3. So it's like this. So I'm going to use the same V1 and V3. So you can see that the set, this is a new set, this set right here is a subset of the hyperedge 1. So hyperedge 2, E2, actually belongs to E1. And you can see it here because you have the overlap. So you can easily figure out that E2 is a, belongs to E1. Now let's do another example so you guys can see. So basically it's very easy. So we said now we're going to do a V2, 1, 2, 4, 1, 2, and 4. And if we do that, so 1, 2, 4, this is our third hyperedge, and let's call it E3. Okay, so you guys can basically do this multiple times. You can see there are overlaps now between sets. So a hypergraph basically allows us to look or examine the graph as a set of overlapping subsets of nodes. Okay, and each subset of nodes, when this subset is together or put together, it will define what we call a hyperedge. So now if we examine further this matrix, you'll see that when you add up these elements, we have a number strictly larger than 2 generally, but you can have or equal because you can have the case of 2, for example, connections like here. So here 2, 3, you have 3. You can also have 4, which means including all edges, and that's all nodes, and that's the maximum number that you can have. Okay, so if we put 1, 1, 1, 1, it means now we have this, all the nodes put together, and this defines actually E4. Okay, good. So that's a hypergraph with hyperedges. So now we will move to the next step, which is, or the next topic, which is the adjacency matrix and its properties. So we'll look at different properties of this matrix. And here's just an overview. This could develop over several lectures, like including graph theory. So you guys, if you're interested, you can watch the graph theory series also. But I'm going to give you an overview of the most important concept just to understand the importance of this adjacency matrix. So the adjacency matrix, it presents the heart